related rates last time. We do more related rates. We do that for a while, and then we'll do some other stuff. And the chalk is broken. There we go. You can tell how well we rehearsed these. Okay, so related rates. As you saw last time, we give you some situation and you have to come up with an equation to figure out how the rate that something is changing is related to the rate that something else is changing. Then you take the derivative with respect to t, dBdt, dAdt, and you plug in. So they're not as scary as they initially look. The tricky part with related rates is the setup. So let's practice some more. The volume of a sphere. Is increasing. At 24 pi cubic inches per second. That's pretty fast. How fast is the radius increasing? This is a basic one. When r equals 3 inches. Okay? So we did one exactly like this on Monday. You should all be doing this. Don't look at your notes to see if you can figure out how to do it. And I know by now you've memorized that the volume of the sphere is 4/3 pi r cubed, so I don't even have to write that down. Okay. Because you don't even have to look. But if you felt like looking, it's over there. Okay? So we'll give you guys 3 minutes.
You can do it. Okay. I see this.
One more minute, and we'll do it together. Still wearing the short sleeve? You're a brave man on a day like today. It's not warm out there. We're over there. All right. So what do? We got a sphere, and the sphere is increasing. So you want to find how fast the radius is changing as the volume changes. Because the radius is related to the volume, and as the volume grows, the radius will grow at a slower rate because you have that amount of volume. An increase to there of that amount of volume might only be that amount for the next increase and the next increase, because each one is bigger. Each one is wider. So the amount of volume in this shell could be the same as the amount of volume in this shell and the amount of volume in this shell. So the radius is going to change at different rates. Okay? And it's related to the volume, that's why we call it related rates. So we have a way to relate the volume of the sphere to the radius of the sphere. That the volume of the sphere is always 4/3 pi times the radius cubed. Okay? And don't let the 4/3 pi scare you. That's just a number. Okay? It's about 4.1. So it's really, this is just a constant, something r cubed. So I want to know how fast it's changing, and I know that the volume dV dt is increasing at 24 pi. I want to know how fast is the radius increasing when r is 3. I shifted from lowercase to uppercase, but whatever. Okay? So I'm going to take the volume equation and take the derivative. dV dt is 4/3 pi times 3r squared dr dt. Okay? So it's an implicit derivative. All of related rates are implicit derivatives. It's always going to be d of a variable dt, unless we do time. Then you get dt dt. Okay? But everything else is d variable dt. So now we just plug in. Notice we cancel those 3's to make the math easier. And you get 24 pi is 4 pi times 3 squared dr dt. The pi's cancel. And you get 2/3 equals dr dt. And 2/3 what? 2/3 of an inch per second. How do we know it's an inch? Because the radius is a linear measurement, it's a line, so it's inches. If we were doing area, it would be inches squared. If we were doing volume, it would be inches cubed. You guys all know units because you take chemistry. Right? We love units. Right? You'll love them even more when you do physics. Right? Summer physics. That's double intensity physics. It's nice knowing you. Okay. So I took a 3-week super session of physics once. It was 8 hours a day. We literally just showed up in the morning, you did physics. So we didn't say there was no homework though. I mean, it was just sort of a giant class of physics. It was great. Really fast. Okay, everybody understand this? Now I'm going to do a slight variation on this to make it a little harder. Can I start erasing? So let's say the volume of the sphere is increasing at 48 pi cubic inches per second. How fast is the surface area increasing when r equals 4? And of course, you don't need to be reminded that the surface area of the sphere is 4 pi r squared. So now, as a clue, what you could do is isolate r in one of these equations and plug it into the other, and that would give you volume in terms of surface area. But that would not be fun, and you'd have something to the 3/2 or something to the 2/3. So you really don't want to do it that way. What you're going to want to do is you're going to set up 2 separate relationships and then put them together. Okay? That sounds scary. It's really not very hard. So just start doing things and see what happens. Okay?
How we doing on this? Okay, got it. All right, 1 more minute.
All right. I'm ready. So this is going to be just like the other one. We got the volume, we got the surface area. The problem is we don't have an easy way to relate volume to surface area. So as I said, you could go here and say, that's R, and then plug that into volume, but that would really be unpleasant. So instead, what you do is you work them separately. This has shown up on exams in the past, problems like this. I don't know why I said that, so I throw that out there. So you got volume, you got surface area. So let's just start with volume. We know that dV dt is 48 pi. We are looking for ds dt when R is 4. So let's plug in. Let's take the derivative of this and we get dV dt is 4/3 pi times 3r squared dr dt. You know, sometimes what you should do is just get in there and start taking derivatives and plugging things in and see if you stumble into the right answer. That'll happen more often than you realize. So you cancel the 3's. And now, if we plug in R, we have dV dt, we can get dr dt. Why would that be useful? Well, if you go over here, you'll get s dt is 4 pi times 2r dr dt. We are trying to find the s dt. We know r, and from here we can get dr dt, and then you plug in and you'll get ds dt. So 48 pi is 4 pi times 4 squared dr dt. Pi's cancel, that's why I put 48 pi to make your life easier. Oh wait, we're catching up. So you simplify this and you get 3/4 is dr dt. So far so good. This is when simplifying is helpful. You could write 48/64, it'll work, it's just messy. Okay, now we go over to ds dt. This is what we're looking for, remember? So ds dt is 4 pi times 2 times 4 times 3/4. So you do a little canceling and you get 24 pi. Okay. And what would the units be? They'd be square inches per second. Why square inches? Because we're doing area. Okay? I don't know if we will expect you to supply the units on the exam. We might. Okay? How are we doing this one? Okay? Yes? No? Maybe? Who got this one? That's a very small number of hands. Okay. The people who took calculus in high school. Not even the people who took calculus in high school. That's not a good sign. All right, let's do a couple more. CD. you got a cylindrical tank, so a tank shaped like a cylinder, and the cylindrical tank is filling with water at the rate of 4 cubic feet per minute. The radius of the tank is 20 feet. How fast is the height of the water rising when h is 6 feet? And we know that the volume of the cylinder, pi r squared, h. Because of course you know that. Because it's pi r squared, that's the circle, times h. That's how high it is. Okay? Let's give it a couple minutes.
Maybe one clue. Think about a cylinder. As water rises in the cylinder, the height of water changes, right? Gravity gradient. So what's the RDT? The RDT is 0. Because the radius is not changing. Okay. Does that make it easier? It makes it easier for some of you. The rest of you, I don't understand what they do. The RDT is 0 because the radius doesn't change. Remember, dEt means the rate of change. 0, and radius is 2. One more minute. Okay. Ow. Yes.
is R is constant. So you have a couple of ways you could do this. First, we erase while we talk. All right. So the volume is pi r squared h. We know that the v dt is 4. We know that r is 20. We want to find the h dt. We're going to use capital H. The h dt is what we're looking for when h is 6. So you could either take the derivative and remember that dr dt is 0, or you could just plug in 20 for r, because the radius doesn't change. Okay? If you wanted to take the derivative, you would use the product rule. You would get pi r squared dh dt plus h times 2 pi r dr dt. But the radius is constant, so the r dt is 0. So the volume, sorry, that's dv dt. So dv dt is pi times 20 squared dh dt. So we actually don't care if the height is 6. So now you just plug in 4. It's 400 pi dh dt. And divide. So 1 over 100 pi. By the way, if you had a problem like this on WebAssign or something, remember the pi is in the denominator. That's the kind of thing that you input incorrectly when you're doing these. Be very careful. Okay? It's 1 over 100 pi. 100 pi is in the denominator. Okay? That one was not so bad. They're all kind of these same kind of crazy questions. So let's do one more. Now here's the type that I really like to put on exams. Of course, I'm not writing this exam, but I can tell you when the last time I did 125, it was on the exam. So it's similar to this, except now we're going to have a conical tank. Okay, a conical tank, a tank shaped like a cone, is filling with water. So the water is coming in. Okay? And the height of the tank is 24 meters, and the radius of the tank is 8 meters. And it is filling at 24 pi cubic meters per minute. That's fast, by the way. You wouldn't want to be in there. How fast is the height of the water rising when the water is 8 meters high? And you guys know the volume of a cone, of course, because I wrote it down last class. But just in case, it's 1/3 pi r squared h. Now we can do this as a team, or you guys can do it on your own. Doesn't really matter. I'll let you take a minute to absorb what's going on. This is so much fun. We'll do it as a team. All right. So what do we know? We know that the height is 24. The radius is 8. Why am I telling you that? I am telling you that for a very specific reason. Okay. In a cone, okay, that's a cone, that's the radius and the height. At any moment, the ratio of the radius to the height is always the same. Okay? So, any radius divided by its height will equal any other radius divided by its height, and so on. You get similar triangles. So, since the radius is 8 and the height is 24, that ratio is always going to stay 3 to 1. That's going to be important. All right, it's filling, dv dt, equals 24 pi. We want to find dh dt when h is 8. So why are we going to want that information? Well, let's go here and look at the volume equation. Volume is 1/3 pi r squared 8. Both radius and height are changing, so if I take the derivative, I'm going to get the product rule. And I'm going to have a term with dh dt in it, and I'm going to have a term with dr dt in it. And the problem is, I don't know what dr dt is. I only know what dh dt. I'm only looking for dh dt. I know dv dt. I don't know anything about dr dt. So how can I get around that? I can use the fact that the radius and the height are related to rewrite the volume equation and get rid of radius. Because I know that radius over height is always 1 to 3. 8 divided by 24 is a third. So the radius will always equal h over 3. So now I can take that and I can plug it in here. And again, volume is 1/3 pi h over 3 squared times h. Okay? Don't be scared off by that, it's not that hard. So V, do a little magical algebra, is pi h cubed over 27. Okay? 3 squared is 9. 9 times 3 is 27. H squared and h makes h cubed. Okay? Take the derivative, and you get dv dt, and you get pi over 27 times 3h squared dh dt. And now I just plug in. So dv dt is 24 pi equals pi over 27 times 3 h is 8, 8 squared, dh dt. Pi's cancel. And I get 27 over 8 meters per minute. And by the way, if you can't simplify that, that's okay. Right? It doesn't matter if you simplify that perfectly or not. That's not what we're testing. We'll try to remind the TAs of that. TAs, are you watching? We'll try to remind them of that when the time comes to store it. All right. Let's do one more. How did we do on this one? We did as teams, so I think we did okay. Let's be sure. All right. You want to stand pretty far when these rockets get launched. A rocket is launched and it takes off. It's going straight up at 4 miles per second. It's pretty fast, right? Yeah, well, once they get going, we're moving pretty fast. After 2 seconds, how fast is the angle of elevation increasing? So, you got the rocket over there, it blasts off straight up, and you're watching it. So you go, wow, look at that rocket. How fast is that angle of elevation increasing? So we're going to give you a couple minutes to see if you can figure it out, and then we'll do it as a group.
Take trigonometry. Trigonometry is your friend. Right? This is a trigonometry one. Okay. You can do it. Where's the guitar? There's the guitar. Okay, so
Yes. All right. All right, a rocket is launched. It takes off, whoosh. By the way, that cloud that comes underneath the rocket, you don't want to be anywhere near that. That's very hot, and it's a very big cloud. So it tends to end things very quickly for anything that's nearby. And you are standing 3 miles away. So you are here, and the rocket's going to go up like that. You really want that to be Pythagorean theorem, don't you? You just really do. But unfortunately, it's not. You are 3 miles away. And this, we'll call this distance x. The x dt is 4 miles per second. And we'll call this theta, because we love Greek letters. So d theta dt is what we're looking for. And we want to find that when 2 seconds have passed, so x is 8. Once the rockets get going, they're going very fast. It takes them a few seconds to build up some steam, and the acceleration and all of that. And if you do physics, you'll realize how fast they have to go. It's pretty fast. Okay. So do we have a relationship between x and theta? Yes, we do. Not sine. Tangent. SOHCAHTOA, right? So opposite over adjacent. So the tan of theta will always equal x over 3. Or if you don't like fractions, which a lot of you don't, 3 tan theta equals x. You don't have to do that step if you don't want to, but you can. Alrighty. There. Take the derivative. 3 secant squared theta d theta dt equals dx dt. Okay. So we can plug in. We know dx dt. We just have to figure out what the secant of theta is. And we know we have a triangle. Well, that's 3 and that's 8. So you do a little Pythag and you get square root of 73. So the cosine would be 3 over the square root of 73. So the secant is the square root of 73 over 3. It's hypotenuse over adjacent. So this is 3 square root of 73 over 3 squared d theta dt equals 4. So you do a little arithmetic, and you get 73 over 3 d theta dt is 4. So d theta dt is 12 over 73. Now what are the units? What's changing? The angle, okay? It's radians per, did I say minutes? Oh, this is minutes, I should say seconds. No, that's the old problem. Radians per second. Remember, never degrees. Okay? Do we like that one? No? No? Yes? No? That was tricky? Alright. I'll give you one more. A runner on first base is heading towards second base. So what does that mean? For those of you who don't know what I'm talking about, in baseball, you have a diamond, and the bases are 90 feet apart, as opposed to the pitcher's mound, which is 6 inches. Don't forget the 6 inches. Okay. You've got the runner who's standing on first. That is a perfect example of a runner. Very lifelike. And the runner is heading this way. Okay? And after 2 seconds, how fast is the distance between home plate and the runner changing? And by the way, these are all right angles. Okay? This is not hard. Just think about it for a minute, you can do it.
What's your favorite theorem? You remember this word like the theorem?
I will post some pages from my book on related rates. No, I'll post some pages on related rates from my book. You're welcome. They will go up. These are the classic examples. If you can do these, you can pretty much do anything. Okay? There's only about a half a dozen different types of related rate problems that we do. So if you can do these, you should be in pretty good shape. Okay? I mean, there's a couple of really evil ones, but I hope they are not on the final. Maybe. All right. Let's look at this for a minute. Let's call the distance between the runner and we're going from first to second base. Let's call that distance x. Okay? And that distance x is growing because the runner is heading from first to second. So dx dt is how fast that runner is going, and that's about 24 feet per second. I'll tell you now, if you're running at 24 feet per second, you're going to be out. You got to get closer to 30 feet per second if you want to have a shot. Unless you're catching mucks or something like that. But you got to move a little faster than that. Okay. So we want to know how fast this is changing at t equals 2. So when x is going to be 48 feet, because you've gone 24 feet per second for 2 seconds. And this is the distance between home plate and the runner. So do we have a relationship between these two? Well, I don't know if they have a relationship, but we can relate the distances. We know that x squared plus 90 squared equals y squared. Right? That's the Pythagorean theorem. So let's take the derivative. 2x dx dt plus 0 equals 2y dy dt. That's a pretty easy relationship. Okay, cancel 2's. You don't have to, but it always makes the arithmetic easier since you can't use a calculator. And we know x is 48, we just need to figure out what y is. So we could do a little Pythag. And 48 squared plus 90 squared equals y squared. Ooh, 48 squared. That's not a fun number. That means 304. 2304? Okay. There's a trick to that. Alright, so that's 10,404. So y is the square root of 10404. We could ask you to do 48 squared in the exam. You just take a piece of paper and pencil and you write 48 and 48 and you multiply. Alright, so we've got 48 times dx dt, which is 24, equals the square root of 10404 dy dt. This problem's a lot easier in meters. Okay? So 48 times 24 over the square root of 10404 is your answer. I don't really care what that simplifies to. Okay? So it's actually very straightforward. So far, so good? Okay, so that's related rates. I actually want to get a little start on the new topic to give you guys a bit of an advantage heading into the homework for next week. Okay, do you understand this one? So all of these is the same problem. You just have to take it from a word problem into an equation. Once you got the equation, it's very simple, right, Jane? Alright. So this is going to be about maxima and minima, which is plural of maximum and minimum. If you think about a graph, remember, derivatives tell us the slope of the graph. We look at the slope of the graph and we say, what do we know? Well, we don't know much, but we know, for example, the graph is going up here. So since the graph is going up in this first piece, the derivative here would be positive. And we did a little of this before now. And we know the derivative here would be negative, and the derivative here would be positive again. And right here, the derivative is 0. Okay? Those are horizontal tangent lines. So if we look at a graph, we know where it has could have maximums or minimums, maxima or minima, by looking at the derivative and seeing if the derivative is 0 there. Now these are what are called relative maxima and minima, because this is a minimum for this zone, but but it's not actually lower than this number. Okay? So that's called a relative maximum or relative minimum. You also have something called an absolute maximum or an absolute minimum. Okay? That's where the real maximum is, because nothing is bigger than it, and the real minimum. So we can use calculus to find these. Why would we care? Well, that's a good question. Oh, you care about it for all sorts of reasons. In the business world, if you have your profit equation, you want to know what's your maximum profit. You want to know what's your minimum cost. In the biology world, you might want to know maximum growth. Okay? In chemistry, you've got all these crazy rates going on. Physics, you launch a projectile, you want to know when it hits the top. So knowing where maxima and minima are is actually very important. That's kind of what we use calculus for. Lots of problems we use calculus for them. So for example, let's say we have your favorite quadratic equation. It's very straightforward like that. And I want to know where the maximum or minimum is for that equation. Okay? By the way, that's a parabola and it's opening up. So it's going to have a minimum. It's not going to have a maximum. Okay. So what do? I take the derivative and find where it's 0. So remember what I told you before. This is calculus class. So when in doubt, take the derivative. Now I'm going to give you the corollary to that. Once you've taken the derivative, if you don't know what else to do, find where the derivative is 0. Maybe that'll be worth something. Okay? So you take 2x plus 8, you set it equals 0, and you get x equals -4. That's called a critical number, or a critical value, depending on the book. So your technique is you're going to try to find critical numbers. Once we know that that's -4, we just need to figure out if this is a maximum or a minimum. And we happen to know in this case, but you want to kind of show it. That's when we say things like justify your answer. What you do is take a number line and put the critical value on the number line. Critical number, sorry. Now pick a number less than -4 and plug it in to the derivative, and if a number greater than -4, plug it into the derivative, and see what happens to the sign. So you take a number less than -4, like -5, and you plug it in, and you get -2. So that's a negative. That means the curve is going down here. Now take a number greater than -4, like 0. When in doubt, you want to try to plug in 0, because it's very easy to plug in 0. You get 8, that's positive. The curve is going up here, that must be a minimum. So your minimum occurs at x equals 4. -4. Okay? Now how do we find the y coordinate? You go back to your original equation, and you plug it in, and you get 16 minus 32 is -16, plus 12 is -4. It's just a coincidence. So your minimum is at the point -4, -4. So we could ask you, at what value of x does this have a minimum? We could say, what is the minimum value? Or we could say, what are the coordinates of the minimum? Unfortunately, I picked one where they both come out the same, so now I'm going to do one where they don't come out the same. Alright, that's something like that. And I want to find minimums and maximums. So rule number 1, take the derivative. Okay, so that's q minus 6x squared plus 9x minus 5. Take the derivative, and you get 3x squared minus 12x plus 9. Okay, take that derivative and set it equal to 0. That factors quite nicely. You get x equals 1 and x equals 3. Since you don't have calculators, I'm not going to give you anything too obnoxious. Okay, so let's sign test this. Pick a value less than 1, like 0. Plug it into the derivative. You get 0 minus 1 is negative 1. 0 minus 3 is negative 3. Two negatives multiplied together give you a positive. So the graph is going up to the left of 1. Remember we asked you in the previous exam, where is it increasing and decreasing? It's the same thing. Now to pick a number between 1 and 3, like 2. You get 1 times negative 1, that's a negative number. So the graph is going down here. So this is where the maximum is. Now you pick a number greater than 3, like 4. Then you plug it in, and you get 3 times 1 is a positive number. The graph is going up again. So that's the minimum. So you have a maximum at x equals 1 and a minimum at x equals 3. Now you just need the y-coordinate. So when x equals 1, half of 1 is 1 cubed minus 6 times 1 squared plus 9 times 1 minus 5 is negative 1. And you plug in 3, and you get 3 cubed minus 6 times 3 squared plus 9 times 3 minus 5 is negative 5. So therefore, you have a maximum at 1, comma, negative 1, and a minimum at 3, comma, negative 5. Of course, you can now graph this, because we love graphing. So we're going to be asking you to do that, just so you know. And of course, we'll make your life terrible by asking you to graph something with trigonometry in it, or equally awful. Maybe not. Okay? So that's enough for one day. We'll do more on Monday. Everybody have a nice weekend. Bye.